So this talk is a little bit of an outlier. Well, there's quite a few outliers. This is a strange conference. QNLP and so many other things are discussed at the same time. So this is going to be very much quantum machine learning, right? Connected to classical machine learning to some extent. And it has to do with all this NISQI stuff, just to give you a heads up on what's coming. And maybe I do have a feeling that there are many experts in the audience. I might be repeating things that you might know, but I'm still going to go through the basics for those who don't have the background in machine learning in general. So bear with me. So I would like to just motivate the talk on why we're talking about quantum machine learning in general. And there's sort of two basic ideas, right? One, which is quite an old idea from the early 2000s, is that sometimes machine learning requires compute power. Sometimes you have to solve well, either a lot of computations or actually solve hard computations. For instance, you're thinking about 0-1 boosting, when you have to select a subset of classifiers, which when combined in the right way, solve your problem optimally. In which case we talk about the combinatorial optimization problem. And you know, this is hard, and there was an idea that maybe, you know, you can Grover speed up the thing, or maybe you can use an annealer and hopefully get better heuristics than you could do classically. This is like 2000 to 2006. And then around the time of HHL, Alessandra was talking quite a lot about it. It was noted that you can try to interpret quantum mechanics as linear algebra in a literal sense, like really as large matrix multiplications applied on a large vector, which may as well be your data vector. And then with an appropriate data access, you can hope for even super polynomial and exponential speedups. So process information in polylogarithmic time in the size of the data. So this was super exciting, right? But somewhere around the time where you and Tang came about and kind of showed that many of these things you can also do classically through stochastic processing rather than quantum, another important thing happened, which is that we had this first serious demonstration of a computation which is arguably beyond what classical computers can do, or at least is doing it in a very different way. And of course, I'm talking about the landmark paper of Google on quantum computational supremacy, which was this sampling problem which was done, which at the time was argued would require 10,000 years in a certain type of a quantum simulator. Not the best one, but one of them. Nowadays, we talk about 3 minutes for the same computation, but that's a matter of scale, right? This was on 53 qubits. If it was 60 qubits, the same arguments of 10,000 years would probably hold. Now, this was said to herald the NISQ era, the noisy intermediate scale quantum, where quantum computers are not fault tolerant. You cannot really do whatever sets of gates you want in whatever architecture you want to whatever depth you want. You're very limited in types of things you can do. And yet at the same time, you have first convincing arguments that it's doing something more powerful than, well, beyond what classical computers can do. And it's very frustrating that we've studied quantum algorithms for 30, maybe even close to 40 years, and then we spend billions, literally, and we get quantum computers that are completely different than the ones we would like to have. Right? We don't know how to use them, and we don't know how to program them. Yeah. So that's the frustration that we're all kind of feeling and trying to get around. So the idea that came about from this picture is to somehow delegate the programming part to a classical device, and to say, hey, Mr. Classical Computer, why don't you play around with the quantum computer and get it to do something useful for me? Right? And this is what's going to touch upon machine learning, because machine learning is all about getting computers to do useful things without providing explicit programming, right? That's what we do. And this is this third flavor of quantum enhanced machine learning that I'll be talking about today, where we're not trying to speed up a classically specified algorithm. We don't really understand the input-output relation we're going to get, but we're hoping that it's interesting and different than what we are accustomed to or can do classically. So it's about having really quantum specified machine learning models. And the main player in all of these works, and they've been applied in machine learning, in combinatorial optimization, in certain types of variational quantum chemistry, condensed matter physics, PDE solving, you name it, people have done it, is the parameterized quantum circuit. Right? So it's a quantum circuit which has gates like any other. Perhaps their architecture is predefined, perhaps they're of constant depth, and maybe I don't worry about how deep it is, but each one of them in principle carries a free parameter that I can tune. So we're not talking about an alphabet from a discrete set, we're talking about a continuous alphabet of gates that I can apply. For the physicists, this would be sort of the duration of the pulse of your field that you apply, that drives your evolution. So I fix this thing. Some of them are, let's say, completely free. They're the things that I will tune in my training. Some of them are going to be input dependent. So I'm going to set my gates depending on what my input is. I will measure some observable, which may or may not depend on the input. That's a separate topic. And the expectation value of the state that this circuit prepares, starting from some fiducial state, relative to a fixed observable, will be the output of my computation. So this is a function, right? It's a function which comes from a family specified by these thetas, which are these free parameters, takes x an input and produces an output, which, given by the Born rule, is exactly this. Is the trace of the observable times the state. Yeah. So the input is some set of tunable parameters. The trainable thing is other tunable parameters of my circuit, and the output is typically the expectation value with respect to some observable. That's the things you see most commonly in literature, and arguably it's sort of the only thing you can have. You can kind of show that this is universal in many different ways, but I will not be worried about that. What I will think about this, I will realize that this is actually a hypothesis family. So now I'm switching my language to machine learning. I'm going to say there's a family of possible functions that I care about. They're my hypothesis family. And if I'm doing machine learning, I will be looking for one which does the job right. You know, what the job is, it might be classification, like cats v dogs, or it could be the right policy if I'm doing reinforcement learning or something similar. So I'm pretty sure that probably most of you know this quite well. So just to get the language down, so I will be mostly worried about supervised learning, like classification. So I give you labeled data, you analyze it, and then you try to understand what is the labeling function, what is the underlying law which assigns labels to data points, with the objective of being able to label things which were not in my data set before, so new points. I will be typically doing this by minimizing some of the training error. I'll be looking at how my model performs on the training data. And perhaps I will also add something which is called a regularization term, which is going to prevent overfitting, right? Because again, I don't care about getting the data that I know correctly. I care about getting the data that I don't know how to label correctly. So this is the error that I do on my data set is going to be called training error or empirical risk. And of course, ultimately care about the total error. There's a hypothetical quantity that I cannot really compute because I don't have access to all possible data points. That is what error would I have if I were to evaluate it on average on the entire space of things that I could possibly have. And the thing that I care about the most is so-called generalization performance, roughly defined as the gap between the training error and the total error, right? So if I evaluate my model on my training set, I get some quality of performance. What can I say about what it will do beyond my training set? This is a scaling thing. It's not a number, it's a scaling thing. You're trying to get this thing down, and it has to do with how expressive your model is. And you can do theory, characterizing just how large this gap can be. But of course, in practice, the results might be completely decoupled from theory, which is why well, we see deep neural networks work, whereas most theory tends to tell you that they shouldn't, that they should really, really catastrophically overfit. And we're still trying to understand that phenomenon. So there's this disconnect between theory and application. And this is sort of what we do in this field of quantum machine learning, for better or for worse. We look at some machine learning application, we find where the neural network is, or whatever the machine learning model is, kick it out, put in a quantum neural network, or this parameterized quantum circuit, and kind of hope for the best, right? That's simply the honest truth of what we do. And then now, of course, as a scientist, you should all object, and you should say, that's not a good enough motivation, right? Tell me why on earth we should do such a thing, right? And the fact is there are deep reasons, right? Number one, let's say pragmatical, is because over time we've learned that models matter, right? The choice of the machine learning model makes all the difference. Again, the key example being deep neural networks, where theory said they shouldn't work until people tried. Data got large. It turns out in the size of the world we're in, they seem to be unbeatable, right? They're the best thing that we have. Whereas a single hidden layer neural network would not do the job just as well. It's a different machine learning model. And further, we have reasons to believe that these quantum models are not entirely uninteresting, as I'll highlight in a second. So two classes of questions that we typically ask. One is, can we get it to work? Can we train them? Do they match the device that we actually can build, and so on? Very pragmatic questions. What happens under noise? Second kind of question, should we get it to work? Do they do anything interesting? What kind of types of these models are there? Are they all the same? Are there different types? Do they perform well? So this is the kind of thing that I want to talk about today. Not the first type of question, but the second type of question. And it just so happens that there are many types that we've studied so far. And roughly, they fit into one of these three camps. Not all of it. There are things which are, of course, outside of this domain in some sense. But these are the three types I want to talk about. So the first one is maybe historically the first one, which is the so-called explicit model. I will motivate why I call it explicit in a second. But it's characterized by the fact that the circuit is split temporally into two parts. The first part of the quantum circuit, which just depends on the data and is not trainable otherwise, and the second part of the circuit, which doesn't depend on the data and is trainable. So there's a clear separation. Quantum mechanically, things don't commute, so if I reshuffle things around, intertwine them, I get something different than this model here. I get something which we call a data reuploading model, where the data can be appearing in the circuit after certain trainable parameters and it doesn't commute through at the beginning. And then in the middle, we have something which is called the implicit model or the quantum kernel model, which somehow doesn't have this trainable part in the quantum circuit. It does everything quantumly, which just depends on the data, and then there's some classical information processing. And these two things, the explicit model and the implicit model, are intimately related, right? So let me briefly reflect on this. For those who come from a classical background, who know about support vector machines, the difference between these two things is essentially whether you're thinking about SVMs being optimized in the primal picture or in the dual picture. That's one way of thinking about it, even though it all generalizes beyond to what we call kernel methods. So what we're really doing is a linear classification. So the way we're going to label data is going to be by finding a hyperplane in some embedding space. And this hyperplane is going to be a thing that we have to figure out in our training process. And once we do, everything which is in one half space is going to have a +1 label. Everything which is in the other is going to have a -1 label. What makes this very powerful is if we combine the idea of linear classification with the notion of a feature space. That is, we don't necessarily expect that the data without any pre-processing allows such a classification. But if we map it non-linearly into a higher dimensional space, then it just might become linearly separable. In fact, there's a theorem showing that you can construct maps which will always make any data set linearly separable, this Covers theorem, even though that's not necessarily what you really want to do. So we have linear classification in feature spaces, two very important concepts. Just one thing to highlight again, the feature map, the thing which maps my data from the original space into this higher dimensional thing, that's not trainable, that I fixed before thinking about the data set that I want to analyze. Now this thing here, this picture lends itself very naturally to a quantum processing thing, because I will simply take the natural Hilbert space of the quantum computer to be my feature space. So I will parameterize my circuit, it prepares some quantum state, it lives in an exponentially dimensional Hilbert space, which is sounding very, very appealing. And in fact, this other part of the circuit that I do turns out to implement a normal of a hyperplane in this high dimensional space. It is not the space of rays, of kets, of vectors. It is the space of density operators, or more specifically, it's the space of Hermitian operators. So my feature space is a 4 to the n dimensional real vector space, not the 2 to the n dimensional complex vector space. And this thing here, which you recognize as the Born rule, is nothing but an inner product, right? So it's an inner product between this vector and this vector, where this is the data, and this is the normal hyperplane, the normal vector specifying the hyperplane. Don't be confused, it's an observable, but it's a matrix. Matrices are also capable of forming vector spaces, right? They can also be vectors. The critical thing, however, is that when I think about the quantum processing thing, the types of normal vectors that I can express here are not all of them. I'm constrained by my choice of the observable, which in particular fixes the spectrum that I can have. And second, the eigenvectors that I can get of the observable depends on the variational part. If this is not an infinitely expressive circuit, an arbitrary unitary, I'm only tapping into a part of the space that I can actually select my hyperplane from. And this turns out to matter, right? If I ignore this part here, then it's just a universal, whatever hyperplane you want in this exponential dimensional hyperplane. And once we understand that there's this encoding part, and then there's a part that I'm looking for a hyperplane, we have to find the optimal hyperplane. There's a primal optimization problem for this. If you look at its dual, it turns out that you can express everything that you want, not in terms of vectors in this higher dimensional space, but in terms of inner products of vectors in this higher dimensional space. So you don't ever have to actually write down the large vector as long as you can evaluate effective inner products. That's the basic idea behind kernel methods, which avoid going to these exponential high dimensional things. It has many consequences. One of them that you don't have to train the quantum device. You can just evaluate inner products, put it in a classical computer, and evaluate things further on. There's a lot of mathematics suggesting that it's the only way that we should be thinking about it, in the sense that we know that in some sense optimal classifiers can always be expressed in this fashion when I just think about the inner products and not the mapped space. I can completely avoid thinking about these explicit models. That's assuming that I don't care about the fact that I cannot really reach all the hyperplanes in the explicit picture. Right? If I forget about this fact, if I pretend that this is an arbitrary complex circuit, then indeed I should probably be thinking about kernels and not explicit models. Now, kernels are very powerful. They're a powerful tool to understand what this type of machine learning does. They also perform really, really well. There's a lot of work in this area. So how bad would it be if this is all there is in the quantum case, if we never have to think about explicit models? And it turns out that, well, it's not very good, in fact. There's a wonderful paper by the Google team called The Power of Data or something or other, where they kind of produce a type of heuristic which tells you whether a data set is going to be better treated by a quantum model or a very simple classical model, where the quantum models are restricted to these kernels. And it turns out that there's this very narrow margin where you can hope for an advantage from a quantum device. So it kind of looks very, well, we would have hoped for more, right? The upside is that there's going to be sort of the main message of one half of the talk is that there is more than that. It's a little bit of an oversimplification, saying it's just kernels and there's nothing else. So this is what we started thinking about. Well, you know, is it really the case that we should only be thinking about the implicit model? Does it matter that these hyperplanes here are not arbitrary? And what can we do about these data reuploading models, which are not expressible as either of the two because of the non-commutativity properties? And now this brings me to the three results that I want to share with you. I will not spend too much time on them. I will refer you to the paper, just the main findings. Number one, these more general models, data reuploading models, can be faithfully mapped onto explicit models. So you give me whatever data reuploading model you wish. I can explicitly, efficiently construct an explicit model which has some part of the circuit which depends on data only, followed by part of the circuit which is data independent and otherwise tunable. And it will be a specific circuit. It will have a certain architecture. And it's I mean, if you know essentially very basic things from quantum computing, it's not surprising. It's essentially using gate teleportation to commute things through where you shouldn't be able to do it at the expense of introducing post-selection, which it turns out doesn't really hurt us in the type of analysis we care about. So these data reuploading models, which are at the face of it strictly more general than the explicit linear models, are not. They turn out to be the same thing, right? But again, it's critical to understand that it is important that we don't get all hyperplanes, that some are inaccessible. If I allow all hyperplanes, I get nonsensical models. And that's in fact the second finding. We show that you can look at these results of Google where they've demonstrated these classical machine learning models perform just as well as the quantum ones, if not better. That's the case if you move to kernels, because kernels sometimes dramatically overfit. And if we stick with the basic explicit picture, this doesn't happen. And then these plots, which again I cannot discuss too much, so these are comparing what the quantum and the classical kernel would do. This is sort of a measure of error in the validation case, so error on the total error, so to say. And this is the full quantum model. So on the same type of experiments that they did, we do the same thing, just don't ignore the fact that you should be dealing with a restricted circuit, and we get much better performance. So message here is not everything is a kernel. Sometimes if you want to have advantages, you really have to stick with the explicit model. And finally, even though we first proved that explicit models are contained in data reuploading models and the other way around, which is the surprising part, there are fine-grained differences between the three. So we construct a machine learning problem in a packed learning setting, probably approximately correct learning, which you can sample efficiently learn using just one single qubit in a data reuploaded picture. So give me a single qubit, and there's going to be a bunch of gates. Some of them depend on the data, some are trainable, and you can train it in such a way that with logarithmically many samples in the dimension of the data, it gets perfect performance. If you want to do the same thing with an explicit model, so that's the one where I first have to do the data input, then I get to process it, you need linearly many qubits in the dimension of the system. And you cannot do it without. If you have less than big omega d, it is going to catastrophically fail. And if you want to do it implicitly, meaning using a kernel, then you need to have exponentially many samples. So in fact, these two guys, the data reupload and the explicit one, they're efficient with logarithmically many samples in the dimension. The kernel needs exponentially many in the dimension. So it's a doubly exponential separation between the settings. And the consequence of this is you cannot simply forget about all three. It is not the case that we can stick with explicit models and that's all we care about. It's not the case that we just should use data reuploading models or just kernels. You kind of have to know what you're doing, which for those who are familiar with no free lunch theorems should not be very surprising, right? For some problems, you have to pick the right tool, and there is no such thing as a fully universal tool. So that's sort of my summary for halfway. From a very theoretical point of view, our main finding is for a broad class of quantum machine learning models built around parameterized circuits, there's one paradigm that captures everything, and that's the paradigm of explicit circuits, where your data comes first, followed by fully variational part. But do not forget the fact that the variational part is still constrained. You cannot implement arbitrary unitaries, you can only implement a certain set of unitaries, and that's very, very important. If you generalize, you get nonsensical overfitting models which are useless for any application. On the other hand, we've also done this fine-grained analysis, looking at the resources, resource counting, learning efficiency, and so on, only to find that not one rules all. It is not the case the explicit model is going to be better than a data reuploading model. In fact, for every case that we've really studied, you really should be using a data reuploading model. It is simply better behaved. It is more efficient in terms of sample complexity. It is certainly more efficient in terms of the number of qubits you need to use to get the same kind of performance. But it might be more difficult to train. For instance, many of you are familiar with Vedran plateaus. They behave slightly differently in the two pictures. So again, not obvious what one should do. It is all situation specific, right? And this is going to be kind of my main message here, is that in machine learning, things are always more complicated than you like them to be, and that theory only gets you so far, and that the proof is in the pudding, and that you really have to apply your thing to a particular problem before you know whether it's any good at all. And that's why, you know, claiming victory or loss for quantum machine learning at this point right now, I personally feel it's a little bit too early to make a call in either direction. So our main challenges are that we need, you know, more theory, of course. Nothing is more practical than practical theory. But we need tests, right? We need to run these things somehow. And this brings me to the second part of the talk, because of course we cannot run these things, right? We need real experiments on real devices, on real data, and that's just too difficult. Why is it too difficult? Because, I mean, come on, we're inventing machines which cost literally billions, exploit, you know, the most exotic theories we've invented in the last 2,000 years. Please do not apply it to MNIST, right? Don't classify something that you can classify with a single hidden neuron thing. Please don't applaud, because I will do exactly that. I will apply it to MNIST, and I will be very apologetic about it, but I will at least admit my hypocrisy at this particular point. So somehow the expectation is if these quantum models that are so super complex, if they make sense, they probably make sense in something which is super complex by itself, right? Not in the easiest task, but in the more complicated ones. Maybe high dimensional, maybe very complex, convoluted, and so on. But we cannot access experiments there, because we have only very few qubits which we can actually train, and even fewer that we can actually simulate, right? So somehow, what do we do? So the idea that we had is you'll see, it's inspired by this idea that you can somehow use a smaller quantum computer to simulate a large one, but I will drop the idea simulate. I will ask, you give me a smaller quantum computer and classical processing, can I mimic in some not fully formal way what a larger quantum computer would be able to do? That's my question. This is our starting point. I call it the circuit shop. It's a result which is well known and studied by many. I think the very first ones were by Bravi and his collaborators in 2016. on trading off classical and quantum resources. So what's the idea? The idea is that, if you take a 2-qubit gate, you can always write it down as a sum of at most 4 products of single qubit gates up to local unitaries. So this thing here, this sum does not have a physical meaning, right? I cannot implement sums of unitaries. I can multiply them by applying things sequentially, but I cannot sum them up. But mathematics allows me to do it, right? And in fact, the number of gates I'm going to get here for single qubit, 2-qubit unitaries, well, one of 3 things. It's either a product unitary, or it's Schmidt rank 2, or it's Schmidt rank 4. These are the only 3 options that are possible. So no more than 4. And in fact, if it's a CNOT gate, which is very commonly used, then 2 suffice. I will have a sum of 2 things, single qubit unitary here, twice. I'm going to add them up with a given prefactor that you can explicitly compute. So that means that I can take my original circuit, I can draw an imaginary line separating into the top part and bottom part, and then this line is either going to cut some entangling gate along the way or it won't. Like if it won't, I'm very happy because in fact I have 2 circuits that I can treat separately, evaluate separately, and then simply multiply the expectation values to get the expectation value of the entire thing. Or maybe I will cut a CNOT here or there. And the moment that I cut it, I can simply express this as a sum of 2 circuits, which have 2 different unitaries acting in the place where the CNOT was. Yeah? We'll have a sum of 2 things. But these 2 things that I'm summing over are now again product, right? So I can evaluate first element of the sum, second element of the sum on this half-sized quantum computer, add them up, voila, I have the outcome that I want. Now, the problem, of course, is that I'm going to typically be cutting more than 1 CNOT, right? And the number of things that I have to sum over grows exponentially in the number of CNOTs. And in the general case, I think this is continuously being improved. I don't want to lie to you. I think the best result a few weeks ago was like 9 to the power of cuts. I think now it's like 4, but I'm not sure. If you ask me, I'll find the references for the most efficient ways of doing it, right? So the thing is, yeah, you can do this. You can cut up your circuit to fit your device. You can do more than 1 cut, of course. It generalizes. But the number of circuits you will have to run grows highly exponential in the number of CNOTs you cut, and the number of CNOTs you cut have to do with how entangled your circuit is and how much it's actually tapping in the quantum effects, right? So it's not a practical thing. You will never be able to run these things, and don't get me started on errors, and God forbid there's a constant error in your thing and everything goes away, right? Nothing works. But I can ask the simple question, but what happens if I don't really use all the terms? Right? Do I really need all of them? Like maybe there's exponentially many terms, but most of them come in with very small weight. Maybe I can ignore them. Maybe there's small errors, right? Maybe there's some concentration effect saying that, well, actually a random sample does just as well. This we don't know. We don't know whether things concentrate. This is related to the sign problem issues for those from more at home in quantum simulation. It is not very likely that I can just randomly choose a subset and be happy with that. But there's a chance that maybe choosing a certain subset, but I don't know which, will be a good proxy for what the full circuit would do in some cases. I'm in the world of heuristics, I do machine learning, I'm allowed to say in some cases. I'm not looking for universal proofs. But even if you give me this, even if you believe me that selecting maybe a polynomially small subset of an otherwise exponential large sum is good enough, I still have to kind of decide which subset. And that's a problem, right? Because now we'd have to select a good one, and this is explicitly a combinatorial optimization problem, right? I have to select something out of an exponential large set that's, exponential choose polynomial. That's my search space that I'm dealing with. So you can forget about it. This is never going to work, selecting a subset. The funny thing is that I don't really have to do that. So there's a lot of text here. I'm going to try to, please don't look at the text, but I still have to speak here. Don't look at the text, look at me. So I have this circuit which was cut, recall, right? I cut in half, and I had a CNOT here. And because I had a CNOT, suddenly the world duplicates into 2 copies, one where I have some 2 single qubit gates appearing here, and then another one where I have another pair of 2 qubit gates appearing here, okay? No longer entangled gates, just 2 qubit gates, but they're different, and that's why I have to treat them differently. But these 2 circuits now differ just in those 2 places, nowhere else. All other gates are the same. So I'm going to generalize the circuit instead of having this fixed gate here, which comes from the decomposition of a C-naught, and make it parameterized. So now for some setting of the parameters, my circuit looks like the left-hand side version, or for you, the right-hand side version. And for other setting of parameters, it looks like the right-hand side version. I've added parameters, but now I have the capacity to represent both. You can do this for every single C-naught you cut. So I can predefine how many terms I want. I know exactly which gates are going to appear because of cutting of C-naughts, and I make them parameterized. So I add parameters to the circuit where there were none. So I'm generalizing the model in that sense. But I'm going to keep only very few terms in the sum. That makes the model weaker. And now, as I'm training the model, since these parameters are free and they can start looking like whatever model I want, the training itself is going to select the subset that I actually want to do. So technically speaking, this is a relaxation of the combinatorial optimization problem that I had before, where as a hyperparameter, I choose the number of terms I want to keep. So what can I immediately say? Well, I can immediately say that no matter what performance I would have gotten, at least with respect to the training part, to the empirical risk, in the full model, in the case that I kept the optimal subset of terms, I can recover the same performance in this model, which has these additional parameters. And because I'm adding parameters, it turns out that the optimization actually becomes easier. Well, it's kind of obvious because I moved from combinatorial to the relaxed version, right, to the continuous relaxed version. So I have a very complex model. I drop a bunch of terms but make it more general. It's not entirely clear what I did to the model, but suddenly I can train it. I can run it on a smaller device. And this is what I mean by mimic, right? It's not the original model that I started from. It is inspired by the original model, under the assumption that exponential sum is not really fully meaningful, that I only need a part of it. It is going to be equally well-performing as the original quantum model. That's the hope. The thing that also happened along the way, by adding these parameters, I'm no longer looking like a quantum circuit. So the types of functions that I have here, which have this parameter zeta appearing here and these lambdas here, they no longer correspond to a larger quantum circuit that was cut up. It's a truly hybrid thing without a quantum analog. If I want to have a quantum circuit which does this, it would become impractically large, right? So it's something different. It's a hybrid thing. But I can still analyze it. So one of the things that I can analyze, I can study is generalization performance, which, by the way, is not a trivial thing because, again, let me remind you, I start with a large quantum circuit, then I cut it up, and I have something which has exponentially many terms in the sum, but this is exactly the same hypothesis family. Then I drop a bunch of terms, so I'm simplifying the model, but I make the terms more general. At the face of it, it's not clear what this did to the model, but if you take any of the standard approaches to bounding the generalization gaps of quantum machine learning models via pseudo-dimension, via the generalized trigonometric polynomials, covering numbers, certain results that we did which have to do with fat-sharing dimensions, it turns out that they're all of them are completely blind to these internal steps. They do not see a difference between this final picture and the initial picture, which is kind of the most boring and problematic result, but also not a bad result. It means that what we got is not worse than what we would have had if we used a full-blown large quantum computer. It is not worse than that. On the other hand, we kind of were hoping that it's maybe better because, maybe this is much simpler than what we had. And in fact, you can do that. You can improve on the bounds that people have studied before by taking into account that these models are smaller, that they're product, that they're sums of products, using certain results involving so-called Minkowski sums, which take unions of hypothesis functions. This is something still under study, but for now, all I can claim is that it's not worse than the model we started from, with respect to any measure that people have studied in the literature who are not us. We can do slightly better than that. Cannot give you quantitative statements for this. We're still working on it. But it's not I would say not an uninteresting thing to do because this thing we can run, right? In fact, we can run models which have 600, 700 qubits and get non-trivial results out of this. Second thing, for those who worry about the training aspects, the Barron plateaus, this is a very particular mathematical structure. It's an additive multiplicative model. That's what they call it in the optimization community. And because I know it looks like this, I can come up with optimizers which are kind of aware where the Barron plateaus would come. and not get stuck where the full-blown quantum circuit would have gotten stuck. So it's never going to be better than the power to train just a single small sub-circuit. Like if that one is impossible to train, then the entire thing is impossible as well. But it can be that the original circuit, the large one, was impossible to train, but the cut-up one that we have is not. That the optimizer now suddenly works. So that's kind of an interesting thing. And of course, it gives you a systematic way of hybridizing further, right? Because right now, still everything is a circuit, but there's no purity police which is going to arrest me if I put one term to be a neural network. I'm allowed to do that. I'm allowed to do other crazy things like compose this with certain wavelet functions and get things which don't have, let's say, Fourier support over the entire space, but maybe it's localized. And we know that it's very important. That's one of the reasons why wavelets are very successful in machine learning, because they're really localized. So you can do that in this picture. We haven't done it, but it can be done. And then we tested on MNIST. And here, I apologize profusely. We did the first thing we could because honestly, well, it's difficult to find a very good data set, but this is a sanity check, right? Can we do the basic thing? Yes, we can. It learns the basic thing, and it does so without dimensionality reduction. So it's simulating a quantum machine learning model over 64 qubits that we don't have. It does it on a laptop. We also try to train models which come from a large circuit. Now, in this case, it's no longer 64 qubits that we're simulating. I think it was something like 20 qubits, but then we chopped it up. And we see a nice cascade. The fewer terms we keep, the worse performance. So this is error. This bottom line keeps 40 terms. The top line keeps only one term. And we get the kind of performance that we would expect. Like if your model is quantum, then you need to keep a lot of terms. If your model is not quantum, MNIST, then in fact the number of terms you kept was essentially irrelevant for performance. This is not a mathematical statement. I'm not claiming this to be true. I'm just observing what we saw in plots. I'm not categorically claiming anything. It's not a theorem. Just an observation which I hope, well, motivates me to do further research here and maybe might motivate others as well to think about hybrid models. So yeah, so I think I've already given the main take-home message that I want to give before. If you want to do quantum machine learning, don't forget about your data and don't forget about no free lunch theorems. It's going to work for something and it's going to fail for something else, which is not an excuse to not do theory, right? We should still do theory. It's going to guide us moving forward. And with this, I would just like to thank my entire team who worked on this, and everything that I discussed is already implemented in TensorFlow Quantum. If you want to play around with it, it's easy to download, and there's a small tutorial that we've done there, and I thank you for your attention.